Juraj Somorowski with Revisiting SSL and TLS Implementations, New Bleichenbacher Side Channel Attacks.
Okay. So thank you for the introduction. So my name is Juraj Somorowski, and today I'm going to show you some new side channels and various SSL implementations. So shortly about me, I am a postdoctoral researcher at the Ruhr University at Bochum, and I'm working for the chair for network and data security by Professor Schwenk. We are doing research in the area of web services, single sign-on, applied crypto, SSL, TLS, or cryptocurrencies. We do some provable security, some attacks defenses, and our chair is a part of the Horst Institute of IT Security, and there are further topics like embedded security, malware, or hard crypto. I'm also a co-founder of our Security GmbH, and within our company we execute penetration tests, security analysis, and give some security workshops in the areas that we work on in our research, so web, single sign-on, SSL, and TLS. And in this talk, I will present you our paper, Revisiting SSL TLS Implementations. The paper was presented this year in August at Usenik Security, and it was done with, written with my co-authors, Chris Meyer, Eugen Weiss, Jörg Schwenk, Sebastian Schinzel, and Erik Teves. And this paper describes new side channels in specific TLS implementations. So it is not, there are not attacks on the TLS specification, there are attacks on specific implementations which are in the wild. Okay, so in order to start with our talk, with my talk, let us introduce first TLS. Then I will go to Bleichenbacher's attack. What does it mean? How does it work? And then I will present our attack side channels and how did they work. Okay, so a TLS intro we had in the morning, and now I will just summarize that TLS was invented about 20 years ago by Netscape. At the time it was called Secure So-Called Layer, and in 1999 it was renamed to Transport Layer Security. We have several versions of SSL TLS, and it is probably the most widely used security protocol in the practice. Because of this, there are several implementations like OpenSSL, GNU TLS, JSSE, Microsoft S-Channel, or Matrix SSL, LibreSSL. TLS provides a secure communication between two parties, client and server. So one can imagine this is really very easy, but in fact, TLS is pretty complex. So TLS contains various cryptographic primitives like RSA, elliptic curves, AES-CBC or AES-GCM, and so on. TLS can be executed over TCP or UDP, and it contains various extensions like TLS renegotiation or the famous heartbeat extension, and so on. Okay, but for this talk, what we need to know about TLS is just that we have some TLS handshake. In our case, RSA-based TLS handshake, which is used to establish secrets between the client and the server for further communication. So in order to communicate, to establish this communication between client and server, the server first sends some client hello, where he tells the server, I'm using these ciphers, I'm using this key, these cryptographic primitives. The server accepts this message, sends server hello, yes, we can agree on this TLS version, on this cipher suite, and he sends a certificate, and server hello done. Based on the value on the certificate, the public key in the certificate, the client can encrypt a pre-master secret for the server. So the client encrypts with the server's public key the pre-master secret, and sends it to the server. This pre-master secret is used for generation of session keys in further communication. Afterwards, the client tells the server, yes, change cypherspec. From now on, we can communicate securely in an encrypted channel. Then the client sends a client finish message, and the server responds with a change cypherspec. Okay, I understand, we can communicate confidentially, and he sends server finished message. Okay, let's come back to client key exchange message. So client key exchange message contains encrypted pre-master secret, and it is encrypted using RSA algorithm. And this pre-master secret is used to derive TLS session keys. This means that decryption of pre-master secret would lead to the decryption of the whole TLS traffic. This is all we need to know. So we need to decrypt this client key exchange message in order to decrypt the whole SSL TLS communication. Okay, let's come to Bleichenbacher's attack. Bleichenbacher's attack was applied on the RSA PKCS 1.5 encryption scheme. RSA PKCS 1 is used to encrypt symmetric keys or other cryptographic material to distribute it using RSA. What is the problem with textbook RSA? The textbook RSA works as follows. So if we would use textbook RSA, we take a message, we execute m to the power of e, which is the public key of the server, and we get a ciphertext. The problem is that if we use the message directly, the message could be short, so it could be guessed, and there is no randomization. So to this end, PKCS1 standard adds randomized padding to the pre-master secret in our case. How is it done? First, the encryptor takes a pre-master secret, so the client, and generates some padding, some random padding, and creates a message 0002, some padding, then 00, and then pre-master secret. And then afterwards, a ciphertext or this padded message can be computed. This message has some randomization, so it is not possible to guess this message, and so we can use it. So this is the structure for a padded PKCS1 pre-master secret, which is padded with a 2000-bit key. So we have here 0002, some non-zero padding, and then 00, and here we have 48 bytes of pre-master secret. Okay, Bleichenbacher's attack. So in 1998, so it was like 16 years ago, Bleichenbacher presented at Crypto his attack on PKCS 1.5. The attack was well noticed in the crypto and security community, and it was applied in different standards like SSL in this time. SSL implementations applied an ad hoc fix to defend against these attacks, and PKCS 1 standard was updated to version 2.0, so-called RSA OAP. But RSA PKCS 1 version 1.0 still remains in practice in many implementations, in many standards. And for example, the newest TLS standard still uses PKCS 1.5. Bleichenbacher applied this attack on SSL TLS. It was in 98. The attack was actually applicable to other standards as well. So for example, in 2012, there was a good paper by Bardo et al. Who applied this Bleichenbacher attack on various hardware security modules or cryptographic keys. It was presented at Crypto 2012. In that year, we also showed how to apply this attack on XML encryption. Okay, so this was our motivation. So the attack worked in 1998, And the TLS implementations and the TLS spec actually claims the implementation could be secured. But we asked, are the implementations correct, and can we apply different side channels, and can we apply the attack? Okay. So in order to present the attacks, I will give you some attack intuition, how the Bleichenbacher attack works. I am trying to not to go much into the detail, so let's see. So how does Bleichenbacher attack works? So imagine we have a client and a TLS server, and we have a client sending client key exchange message, this RSA encrypted message. Bleichenbacher's attack is an adaptive chosen ciphertext attack. How does it work? So in our case, the attacker somehow eavesdrops this RSA encrypted message. He modifies this message and sends it to the server and uses the server as an oracle. And for this reason, this attack also is called padding oracle attack, one of the padding oracle attacks. And the server, the oracle, decrypts the message and takes a look at the message if it starts with 0002 in our case, and based on this, it responds to the attacker with valid or invalid, based on the message validity. The attacker chooses several ciphertexts, repeats it several times. The oracle answers with a valid or invalid, and at the end, the attacker can decrypt the whole message. This is a general scenario for adaptive chosen ciphertext attacks, and maybe you know attacks by Rizzo and Duong. They applied similar attacks on the CBC scheme. This is an attack on RSA PKCS 1.5. So, okay, so I told you we have to adapt somehow the ciphertext. We have to modify them. What do we do with them? Actually, in RSA, it is possible to multiply the plaintext, the encrypted plaintext, without knowing the decryption key. This is very specific for RSA crypto system. So the attacker can take some ciphertext, which should be decrypted to M, but he can construct some different ciphertext, which is M times S, which is S is his value he chose. I'm not going into detail into RSA. If you need more explanation, just grab me by drinking coffee or, yeah. Okay, so what is the attack approach? So we multiply the plaintext, the underlying plaintext, by S value, and query the oracle if the decrypted plaintext starts with 0002. Let's imagine we have, there's an axis of values. The 0 is the minimum value, n is the modulus value, so the maximum value we can achieve in our plaintext. And somewhere here we have our 0002 and the maximum 0003 interval. So somewhere here is our secret that we are searching for, yeah. And let's say the secret is in the near of 0003. So what happens if the attacker multiplies this secret and sends ciphertext to the oracle? So he multiplies it by 2, then it is jumped into the interval to the right. Then if he multiplies it the message by 3, then it is jumped right above, and so on and so on. And when we come to the end of near n, and we jump further, a modular reduction in RSA is executed, and we jump back into the interval 0002, and the oracle tells us the message was valid. Yeah. So we choose S is 2, S is 3, and so on. We multiply the original value until the modular reduction is executed, and we jump into the interval. Afterwards, the oracle answers the message was valid again. Okay. Let's assume the message was in the near of 0002. If the message was in the near of 0002, the jumps are much smaller. So, but sometimes we get into the, again, into the modular reduction, and we get into the interval 0002, 0003. So, and again, here, the oracle responds, the message was valid. So this is just an intuition behind the attack. So if the original value is in the near of 0003, then we have a small s value. Or again, if the attacker needs a small s value for achieving a valid plain text, ciphertext, then he knows that the original value was in the near of 0003. Otherwise, if there was as large as value, then he knows that the value was somewhere here in the near of 0002. This is just intuition behind this attack. And the full algorithm searches for further S values and reduces the interval. Okay. I can show you some, yeah? Three question mark section. Oh. Yeah. How much bits you mean? You mean how many bits I am missing? So how many bits I'm trying to guess? So we know that this starts with 0002. The modulo is like n is can be like 10,000 times larger than this number, about 10,000 times. So we need about 10,000 requests to get again into this interval. I can show you, so we can see, we can watch our demo. I mean, this makes a bit clear. So imagine there is our S value. We are increasing, and this is our minimal interval, what we set on the beginning, and this is our maximal interval. So somewhere here between these two values is our number we are searching for, and we are increasing the S value, sending the ciphertext to the oracle, and the oracle, until the oracle tells us the message was valid, and based on the oracle response, we can narrow down the interval. So in this case, it lasts a bit longer, so we need about 40,000 queries now. So this, but now we found a solution, and we could narrow down the interval. So let's see, we are now, the minimal interval is 0002, F9, F5, and we have now 0002, F9, F7. So we reduce the interval the original value lies in. Then we get, actually the first round is really lasts very long, but afterwards, the next rounds, this based on the Bleichenbacher attack algorithm, are much more faster. So we can see with 40,000 queries, we can reduce down the whole interval that we get only one value left. And this is our solution for the decrypted plaintext. Okay. So, good. So what we saw is that by sending ciphertext to the TLS server, and if TLS server responds with different error messages, the problem is we can get an oracle. which responds with true or false based on the message validity. This is bad. So the countermeasure is pretty trivial and is described in the TLS specification. What we need to do, we generate at the beginning a random premaster secret. We decrypt the ciphertext, and in case the message does not start with 0002 or there is some, the message is of invalid length, then we use this random number and we compute, we proceed TLS handshake with this random number, otherwise we use the decrypted message. Yeah? This is the countermeasure, so instead of returning an error, we just use a random number and we proceed with this one. Okay. Let's get to the attack performance. The attack I presented now lasted about 40,000 queries. If you know Bleichenbacher's attack, it was called also million messages attack, but the attack performance varies. It depends on, the attack performance depends on the Oracle message validation. What does it mean for us? So imagine we have a ciphertext which is sent to the Oracle, and the Oracle can now validate different bytes and send different errors based on this message. So it can, for example, validate if the message starts with 0002. This would be perfect. But there is also, maybe it accepts messages which are non-zero padding, or maybe it checks some 00 in the middle. And what you need to know for now is Oracle with let's checks brings better performance. Why is it needed? So imagine we executed our attack where we used some S value which jumps into this interval, but the Oracle makes more checks and responds with invalid. This means we have to go further and search for next S values, and we cannot reduce the interval. That's the matter. The attack lasts longer. Okay, this is just an intuition way. Less checks brings better performance because, yeah. Okay, so we saw how the attack in general works. We saw how the Oracle works, and what are now our challenges for the current SSL TLS implementations. So our challenges was use some TLS server and use some TLS client which uses the TLS server as an Oracle, and we have a Bleichenbacher attacker which sends to the TLS client some ciphertext, and the TLS client executes some TLS handshake, and based on the TLS handshake, if it is valid or invalid, the TLS client responds to the attacker if the message was valid or invalid. And if there is a possibility to distinguish valid from invalid messages, we can apply Bleichenbacher attacks. We can execute this using direct error messages or using maybe timing. Okay, so our goal is to analyze the Oracle strength. So if there are some differences in the server behavior based on the message validity, if there are some differences, analyze the probability and the Oracle strength, and if there is a timing side channel, how many server requests do we need here to distinguish valid from invalid plaintext, ciphertext, and then execute Bleichenbacher's attack. The research was executed with the help of the library or framework called Time, which is described in the thesis of my colleague Chris Meyer. And yeah, it supports some features like SSL/TLS fingerprinting and so on and so on. And for timing measurements, we used a matrix SSL client library because time was written in Java and was too heavy, and we used matrix SSL library with our Bleichenbacher framework to execute attacks on TLS servers. And we distinguish valid from invalid response times based on the NetTimer library written by Sebastian Schinzel and his students. Okay, so we have some prerequisites now. Let's come to the interesting part and to the attacks, to present the attacks and the side channels. Okay, so first, side channel were error messages in JSSE. JSSE is, as already today morning explained, is a Java secured socket extension, and it's the standard Java library for SSL TLS. And we provided an JSSE server, and with differently formatted messages, we executed TLS handshakes. And we found out that this server responded with 2 errors based on the RSA PKCS1 validity. Yeah? More concretely, if the message started with 0002 and there was some 00 inserted at specific positions in the message, in the decrypted message, there was an internal array index out of bounds exception which led to a different error message. So more concretely, we can see there is a padded message with RSA 1000-bit key. We can see that if the message started with 0002 and there was 00 at this position, the server responded with internal error. This was interesting because in 2000-bit keys, by using 2000-bit keys, we had more positions which provoked this internal error, and 117 bytes provoked internal error, and by 4000-bit keys, we had about more than 300 bytes provoking an internal error. So we were able, based on these error messages, handshake failure and internal error, we were able to construct an oracle. If there is an internal error, we know that the message starts with 0002, definitely, otherwise the message was invalid. So this was our oracle that we could create. So my question is now, so which was the strongest oracle? Okay, so the strongest oracle with which keys? The strongest oracle was actually the oracle which used the server which used 4000-bit keys, because the probability that we get here an internal error is much larger than here by 1000-bit keys. So by the probability by 2000-bit keys, we with probability 35%, the messages with 0002 were indicated as valid. By 4000-bit keys, the probability was much higher. By 1000-bit keys, it was like 0.2%. We evaluated practical Bleichenbacher attacks, and we found out that, as our analysis told us, 2000-bit keys, we could execute Bleichenbacher attack with 37,000 server queries, so we could decrypt a PKCS1 message and the pre-master secret and decrypt the connection. And for 4000-bit keys, the number of queries was much lower because the probability the oracle was stronger. Okay, so there's an example of our attack execution, so we can see, yeah, the pre-master secret which is decrypted by our attack. The attack on 1000-bit keys was not possible because the oracle was too weak and we would have need much more queries. The issue was patched already in 2012, so the attack is pretty old. Okay, let's get to the second side channel, additional random number generation. I already presented the recommended countermeasure, which is recommended by the TLS specification. So it is needed to generate a random pre-master secret, and then in case there is something going wrong, proceed with this randomly generated secret. We saw in many implementations that this was implemented like this. So we decrypt first the ciphertext, and in case there is something wrong, we generate a random pre-master secret. Yeah. So the random number generation is executed only in case something went wrong. We saw this in OpenSSL, GNU TLS, Java, and so on. And our question was, is it enough to execute practical attacks? So we can see random pre-master secret generation is executed only in cases when the message is invalid. So can we observe some timing differences between valid and invalid messages and observe this random number generation? And yes, the answer is yes. We could detect 2 microseconds of difference. So here invalid secrets sent to the server, and here valid secrets sent to the server. And on the left, we can see the number of milliseconds it lasted. And we can see a timing difference is about 2 microseconds between these 2 secrets. There were actually 2 problems with this side channel. We have a very, very small probability we can achieve this, because the probability that we get a good ciphertext is very, very low, and these 2 microseconds were also very low, so we were not able to execute practical attacks. We can distinguish valid from invalid ciphertext, but there was no possibility to apply the whole Bleichenbacher attack. Okay, maybe there is something different in different implementations. So again, JSSE. As we measured the previous vulnerability, the previous side channel performance, we saw that there is also a different side channel in JSSE. And then after a code analysis, we found out that it comes from a PKCS1 unpadding function, which behaves as follows. We have some unpad version 1.5. It checks some bytes, and if it is not compliant, PKCS1 compliant, it throws a bad padding exceptions. Otherwise, an unpadded text is returned. This bad padding exception was not sent to the client, so this was not possible to see direct error messages. However, an exception generation is lasts pretty long. So we tested JSSE server, and we saw this bad padding exception in the message log, but we can't see this from the client. But we evaluated that an exception generation in Java lasts about 20 microseconds. So we were able to distinguish invalid messages with additional bad padding exception from valid messages where no exception is generated. And this lasted about 20 microseconds. So we were able to measure it over LAN and to create an oracle from this side channel, and which had a pretty good probability of 60%. And we were able to construct a real attack in a LAN. So again, we evaluated the whole Bleichenbacher attack. We created our scenario. There's a Bleichenbacher, there's a matrix SSL library, and our server, the matrix SSL library has to send several messages to the server to distinguish valid and invalid based on the timings. But we needed about 500 queries to distinguish them, and we needed about 20,000 queries to decrypt the whole pre-master secret. We got about 20% false negatives, and it lasted about 20 hours. This was patched in January 2014, and we found similar behavior in Bouncy Castle, not only in Java, but also in C# implementation. Okay. Okay, so this was an exception generation, and we found also the last one is the last side channel is based on a specific hardware appliance behavior. We had a possibility to execute the attacks on our IBM data power, which we have in our lab. And we found out with our time framework that the data power does accept different ciphertexts, which does not start only with 0002, but also with 01, 02, 02, 02, 03. So the first byte was not validated at all. And we could execute the complete TLS handshake with invalid PKCS1 messages. Okay, so this was not directly exploitable because the attacker cannot send valid client finish messages, but we thought about it, and we thought there must be some leakage in the PKCS1 processing. So we did a black box analysis because IBM data power, there is no source code available, of course. And we found out that there is a timing difference of 15 microseconds. And we can distinguish, so this is an invalid message which lasts 15 microseconds shorter than valid message. And we were able to construct an oracle which responds with valid in case the message starts with 01, 02, 02, 02, and so on and so on. And otherwise, the message responds with invalid. The oracle was not Bleichenbacher compliant because it does not respond with 0002 message validity, but we extended the attack. The performance was actually improved, and we were able to execute the wall attack with 4,700 oracle queries, and our real attack in our lab was with about 4 million server queries at total and lasted about 40 hours. We tested it with IBM data power. The reason for this was actually that IBM data power used some Cavium accelerator chip, which was used also in other devices like F5 firewalls and so on, and we proved that it works also for them. Okay. Let's come to the conclusion. So we showed first practical Bleichenbacher attacks on TLS with different timing behaviors, with different side channels, and we showed, for me, the most interesting part was that an additional exception can lead to a side channel of 20 microseconds, which is visible in a local area network. And we actually showed that a tiny side channel can lead to catastrophic results. This is very important not only in LAN environments, but for example also in web. Now, Web Crypto API, for example, uses crypto in browser, so the attacker can actually execute the attacks like in on the local host. So we motivate with our work for the usage of secure primitives like RSA OAP, and our future work is do some analysis of further crypto standards and development of further penetration test tools. Okay, thank you.
If we're quick, we can take 1 or 2 questions.
All right, thanks. Most of your Bleichenbacher attack variations were basically based on the timing oracle, as you said. And you got some pretty impressive numbers in percentage based in a lab setup. But when dealing with production systems, basically you'll have things like network latency or server load that will influence the timing, and thereby will influence the oracle and the helpfulness of the information that the oracle provides. Do you have any numbers on the applicability of these attacks under production use?
Actually, the attack on JSSE was in a local environment at a university where actually it was in production system. So there is other trapping going on. So this could be considered as production system. In case of data power, I do not know how to. We did not test it under normal circumstances, but we have to admit these attacks are not like Heartbleed or something like this, where you can get some private keys and so on, like very similar. These are more research attacks, but still you have to consider them. So, for example, if you have an administrator who has no access to the device keys, but can steal the device and execute the attacks at home, for example, steal the device for like 1 day, execute the attacks, decrypt one key, and this could be a considerable scenario. Maybe the attacks can be fine-tuned also in production systems, but we did not consider this in our work.
Okay, we've run out of time. Thank you, Juraj.